Controller design for a TS fuzzy model, common input matrix. This is the 5th lecture in this 4th module on fuzzy control. In previous 3 classes, we discussed mainly the Mamdani type of controllers. Today onwards, we will be talking mostly on TS fuzzy model. Okay, what is TS fuzzy model? What is common input matrix? They may be very new to you, or some of you have some understanding, but we will learn in detail what they are. So, topics that we will be covering is our TS fuzzy model representation of a nonlinear system, identifying the parameters of the local linear models, stability analysis when the subsystem have a common input matrix, controller design and simulation results. So, representation of a nonlinear system. If I am looking at a nonlinear system in discrete time, then usual way approach is x is my state space, n dimensional state space, x k plus 1 is f x k u k and y k is h x k u k. Okay. So, this is our normal function description, and f is n dimensional function vector, h is again m dimensional output vector. So, I have m output and n state, and u is p dimensional input vector. So, the above system can be effectively modeled by fuzzy merging of equivalent linear system in different operating region using Takagi-Sugeno fuzzy model. So, what is meaning of this is that a Takagi-Sugeno model, fuzzy model of a nonlinear system is that although the system dynamics is nonlinear overall, but locally the system is linear. So, by fuzzy merging of these linear subsystems, okay, we can construct an approximation of the actual nonlinear dynamics of the system. So, this is a typical TS fuzzy model. A TS fuzzy model is composed of m rules, where jth rule has the following form: R j, the rule j, if x 1 k is f 1 j and so on, that is x 2 k is f 2 j until x n k is f n j, then that means in the jth fuzzy zone the system is represented by a linear system. Okay, in discrete time here we have written, it can be also written in continuous time. So, x j k plus 1 is a j x k plus, sorry, this is mistake, this is not there, x k plus 1 is a j x k plus b j u k, and y k is c j x k plus d j u k. Because x k plus 1 and y k, they are the system states, we can't put j there. J is affiliated to the coefficient, that system matrix A j, control matrix B j, this is your output matrix C j. Okay. So, the where x is x 1 x 2 until x n, n dimensional vector, and j equal to 1 to m, that means I have m, capital M fuzzy rules. Given a current state vector x k and input vector u k, the TS fuzzy model infers x k plus 1 as. How does it matter? Because we have to finally say what is x k plus 1. So, x k plus 1 is the fuzzy merging or fuzzy blending of output of each system. So, output of each system is sorry, x k plus 1 is here is a j x k plus b j u k. This is my the jth system dynamics, and I multiply with that the corresponding mu j, the membership function. You know, this membership function normally is derived either minimum of the membership function associated with the f 1 j 2 until f n j, or product of them. We can select any one of them, but whatever it is, that is mu j. You select one principal and then find out what is the mu j, the membership function inferred for the rule. Okay. See, membership function is always given a crisp value x 1 k, I know what is the membership function from f 1 j. Similarly, given a crisp value x n k, what is the membership function? The membership function associated with x n k is computed from f n j, but the membership function of the rule is mu j, and this mu j is either minimum of these membership functions that are computed, or you can say mu 1 x 1 k into mu 2 x mu 2 x 2 k until mu n x n k is mu j. We can do that also. So, once I do that and I sum it over from all the rules from 1 to m divided by the summation of all this membership function mu j that we have already computed, j equal to 1 to m mu j. So, this is how we, so first a TS Fuzzy model, we have m rules, and this is my jth rule, and for jth rule this is my x k plus 1. I multiply with corresponding membership function associated with the rule, and then I sum such quantities for each rule from 1 to m, and then I divide that quantity by the summation of all the membership function, that is mu j. And similarly, this was x k plus 1 before 1, and y k is similarly mu j y j, this is not y j, y k, j equal to 1 to m until j equal to 1 to m mu j, where mu j in this case, we have selected in this paper as a product, but you can also take as a mean. It is all up to you, the designer. So, mu j I x I is the membership function of the fuzzy term f I j, j equal to 1 to m. So, the overall fuzzy system can be simplified into, okay. So, overall fuzzy system, that is overall fuzzy system was this one, x k plus 1 is this quantity. This is my the fuzzy dynamics of the fuzzy dynamics representation of the nonlinear system in terms of fuzzy dynamics. Okay. So, this fuzzy dynamics can be written in terms of x k plus 1 is a bar x k plus b bar u k, where a bar is sigma j a j, j equal to 1 to m, where sigma j is mu j upon this. You can easily see that it is very simple. If I rewrite this equation, I can easily write down this. This is simply, you see that I can write this one as a j. So, I write this as a bar x k b bar u k, where this a bar is you see that sigma mu j by this quantity, I can define sigma j equal to 1 to m mu j, this quantity. So, all that I am doing this mu j I am dividing by this total summation, which is this, and the summation is j equal to 1 to m, okay, aj. So, this quantity is, if I represent as sigma j, so I am writing a bar is j equal to 1 to m sigma j aj. So, this is what exactly we have done here. X k plus 1 is a bar x k plus b bar u k, where a bar is sigma j a j, and we defined here sigma j a j, j equal to 1 to m. Similarly, b bar is sigma j b j, j equal to 1, c bar is sigma j c j, j equal to 1 to m, d bar is j equal to 1 to m sigma j d j, and I already defined what is sigma j before, mu j upon the total summation. And you must recognize that sigma j from 1 to m, this is most important, this is always true. The total sigma j has to be 1. Okay. So, the overall system is nonlinear. So, you can easily see that this is a very convenient form, although I am representing this in a state space format, it appears to be linear, it is not linear, because a bar is a function of sigma j, which you see here, and sigma j is a function of x k. Sigma j is a mu j, and mu j comes from x j. Okay, this is a function of x k. So, just like we did for continuous time, discrete time, similarly also we can say for continuous time, instead of x k plus 1, I will write x dot is a bar x plus b bar u, where again x is n into 1 dimensional vector, and y is your whatever we wrote earlier, m into 1 dimensional vector, and u is p into 1 dimensional vector. Okay. And similar, the whole thing again is similar, a bar is sigma j a j, and b bar is sigma j b j, c bar is sigma j c j, and so forth. What we said is, until now we just said what is T.S. fuzzy model, right. Now, given an actual nonlinear plant dynamics, can I directly write what should be the T.S. fuzzy model? It is actually simple. So, the linear model parameters. So, how do I find out for each rule what should be my individual linear system? So, to find out what is individual linear system, one of the method is linearization. So, the linear model parameter a j's and b j's can be found by linearizing the nonlinear system dynamics. This is simple. Example is, suppose the nonlinear dynamics is given as x dot is f x u, which is f x plus g x into u, this is one form, and that can be written as say x plus x square plus u. So, this is your f x and g x is 1 here. The aim is to find a and b such that in a neighborhood of operating point x naught, f x u equal to f x plus g x u, which is x plus b u. Okay. So, how do we find out that? So, when x naught equal to 0, a is dou f upon dou x, x equal to 0, u equal to 0, and b equal to dou f by dou u, x equal to 0, u equal to 0, using Taylor series expansion. This thing we already know, that how we given this nonlinear function f, we can find out this a and b simply differentiating the f by x. Okay. So, when x naught is not equal to 0, and if a I transpose denote the ith row of a, then a I is dou f upon dou x, x equal to x naught plus f I x naught minus x naught transpose dou f upon dou x on x equal to x naught upon x naught norm whole square into x naught b equal to g x naught. Okay. So, the reference you can find out this reference is systems and control given written by Jack. There are many other classical textbook you can follow how to linearize a nonlinear system. I think also we covered this notion also earlier in the class. Thus, two rules of the T S Fuzzy model using T S Fuzzy model. So, our system was x dot was x plus x square plus u. You can easily see that x plus x square plus u. So, that is our system. So, rule 1, if x equal to 0, x dot is so I differentiate this with respect to x. So, I get 2 x plus 1 at x equal to 0. So, if I differentiate this quantity 2 x plus 1 at x equal to 0. So, this will give you 1 x equal to 0, the value is 1. So, into x. So, x plus u, because dou f by dou x at x equal to 0 into x plus actually delta x, but since the operating point is 0. So, delta x is same as x plus dou f upon dou u. So, the since the coefficient here is 1, dou f upon dou u is 1 and into u. Okay. So, a 1 is 1, b 1 is 1. Similarly, if x equal to 1, then we implement the second one, because when x not equal to 0, then we implement this rule, and by implementing that we get x dot is 2 x plus u and a 2, that means a 2 is 2 and b 2 is 1. This is simply a scalar system, scalar differential equation. Similarly, this same thing can be also duplicated to the vector differential equation. So, the linear model parameters A's and B's can also be identified. This is the first method was by simply linearizing. If I know a nonlinear system dynamics and if I think that is an exact model, the best way is to not to waste again system identification, simply linearize this system around various operating zones. Okay. Define the fuzzy partitioning and then do the linearization. But the linear model parameter AJS but this also can be identified using a fuzzy neural network. So, from the input output data of the system, I have given a system, I generate input output data, train a fuzzy neural network. So, when using a fuzzy neural network, the elements of AJ and BJ are weights of the neural network. Least square cost function is used to find the proper weights. Weights are updated using the standard gradient descent algorithm as well. So, this is simple. So, what is that? These are my states x 1 k, x I k, x n k until. So, these are my states and I have m rules, okay, and corresponding to each rule I have a fuzzy membership a linear neural network whose input is x k and u k and output is x k plus 1, output is x k plus 1. So, similarly, corresponding to each rule I have a linear neural network, and finally, we do the defuzzification to compute what is the actual x k plus 1. So, this fuzzy neural network also can be used to derive the T S fuzzy model of a nonlinear system. So, we identify that, and this is my if these neural network weights once after identification they become because for example, this one is the linear model for the rule 1, this one the linear model for rule j, and this one is the linear model for rule m. So, see earlier in the beginning of the class we said T S fuzzy model. I hope that you understood by this discussion. Now, we also talked in the beginning common input matrix, you see. So, what is this common input matrix? Now, you see that the discrete time T S fuzzy model was given by x k plus 1 is a bar x k plus b bar u k, and continuous time of t is Fuzzy model. Similarly, x dot is a bar x plus b bar u, where a bar is sigma j a j summation over all rules. Similarly, b bar is sigma j b j over all rules. But this system you will have a common input matrix when b j is b for all j. So, where b is a constant matrix. So, if I can define the system dynamics in terms of a common input matrix B, B is a constant matrix. If I do that, then I can always design that gives us certain advantage. If so, what I am trying to say is that for if x is some fuzzy zone, then if my state vector in a specific fuzzy zone j, then all that I am saying is that my x dot is a j x plus b u, not b j, b u, and where is a b is a constant matrix. So, this is called common input, and this B matrix is same for all the rules. This B matrix is same for all the rules. So, when this is done, then such a system is known as a TS Fuzzy model with common input matrix. Input matrix is common for all linear subsystem. Why we are interested in such a system? So, let us take a ball beam system. In ball beam system, the ball and beam system is a nonlinear system. The beam is made to rotate by applying torque at the center of rotation. The ball is free to roll along the beam. The ball position and beam angle are denoted by r and theta respectively. The dynamics of ball and beam system can be represented with a state vector x 1, x 2, x 3, x 4 as r r dot and theta theta dot, as x 1 dot is x 2, x 2 dot is b, x 1 x 4 whole square minus g x 3, x 3 dot is x 4, x 4 dot is u, y is x 1. So, single output and single input. If the above system is linearized around a different operating points, all subsystems will have a same input matrix, which is B is 0 0 0 1. This is important. So, by making V equal to 0 0 0 1, this linearization of the system dynamics will always lead to B matrix for all subsystems, linear subsystems. The B matrix is always 0 0 0 1. This is a practical example. Okay. There exists a physical system for which for all linear subsystems the matrix control matrix is 0 0 0 1. Okay. So, that is common. So, utility of common input matrix. What is the advantage of common input matrix? Of course, when B's are same for, that means there must be some advantage, because system is now simpler. Suppose we design individual linear controller for individual subsystem. Okay. I have that say because now I have m linear subsystems. Okay. So, controlling the complete nonlinear system means they involve controlling m subsystems, capital M subsystems. So, now I am saying okay, now you have the freedom to design, because linear system means for any linear system we know where we have adequate technology or adequate tools, adequate methodologies for designing controllers. So, what we are doing here is that let us design control action for each subsystem. So, the control action corresponding to the j subsystem is denoted by u j k, that stabilizes that subsystem. If all linear subsystems have a common input matrix B, then an overall control input of the form u k is sigma j u j k Okay. This will ensure that individual subsystems are excited by their respective control inputs. This can be established by the following theorem. So, what I am trying to say, see, this is my actual plant. I give u and I get x, the response, right, to the plant. Now, I have these are all the apparent subsystems, linear subsystems. This is, and fuzzy merging of these linear subsystem linear subsystems gives us the actual plant dynamics. So, controlling this u means I give to the plant only u. So, that is obviously my input to this plant, to this subsystem also should be u, but instead what I have done, I have stabilized this by giving a input u j, but I cannot give this u j to the plant, plant is given u. But if I can compute this u in terms of u j using this formula, okay, it says that if I have a common input matrix for all the subsystem, then such a control action u k, which is written in terms of individual control action u j, implies that individual control subsystems are excited by u j k. So, this is a theorem. For a class of T s fuzzy system with common input matrix in all fuzzy zones, the actual control action u k will imply that jth subsystem is excited by the control action u j k for all j, where u k is the fuzzy blending of all individual control action. You must recognize this u j is actually fake, we do not apply to any actual system. This u j is simply a control action that is given, that is that means if I give u to the actual plant, it implies this plant is experiencing a control action not u, but u j k. This is important. So, if I am giving a control action u k to the actual plant, individual plant are not being excited by u k, rather u j k. This is very important. Only if the all the subsystems of the T s fuzzy model are having a common input matrix, otherwise not. This is the important. So, the fuzzy dynamics of a common input matrix can be represented as x k plus 1 is that we have already shown, that sigma I a j equal to 1 to m, which is a bar. Similarly, sigma j b, not b j, because common input matrix j equal to 1 to m. Okay. So, we expanded that. Now, you can write this one, I can club this j equal to 1 to m sigma j a j x k plus b u u k. This is the total thing. Sorry, this is not total. So, this is my one term, and you can easily see this term is actually 1, sigma j equal to 1 to m. Hence, this is simply b u k, where b is the common for all linear subsystems. Substituting the control input u k. So, what is u k now? U k is j equal to 1 to m sigma j u j k, and here I can separate this term. So, j equal to 1 to m sigma j a j and x k. Okay. So, this is my a bar, okay. And so we started with, we gave a input u k, which is summation of this individual thing. Now, we will rewrite this equation, then you see that x k plus 1 is sigma j a j x k plus here I can bring this quantity to this side and b inside, simply b I put inside because this is anyway common. So, b inside and use a k. So, doing that, what I am trying to do is that here this is actually again this quantity is 1. So, now what we are doing here is that this, now we have this total thing. that is I can rewrite j equal to 1 to m sigma j and aj x k here, and the sigma j is common here and b u j k. I can rewrite that. So, what is meaning of this? Meaning of this is that this is a fuzzy combination of a j x k plus b u j k. So, individual system is actually excited by u j, when actually I have excited the global system by u k. So, what I showed in this theorem, that if I give u k to my actual system plant, this implies my linear subsystems are being excited by u j. That is the meaning of this. That is the meaning of this method. So, it is clear from the above equation that jth subsystem is excited by u j k, hence proved. Corollary: if jth subsystem can be stabilized by control action u j k, then the actual control input can be computed as u k is this sigma j equal to 1 to m sigma j u j k, and it can be analyzed whether this control action stabilizes the entire Ts for the system. This approach is not valid when the subsystems have different input matrices, which is very important to have. So, when the subsystems have a common input matrix, Ts fuzzy model dynamics. So, closed loop system dynamics with common input matrix. When so I explained to you that what is meaning of common input matrix. Common input matrix means that if the actual plant is excited by capital U k, then the actual subsystems are excited by the individual control action u j. So, that gives us a fairly good method or a good tool for us to design linear controllers. So, now for such common input matrix, what will be the closed loop dynamics? Now, Ts fuzzy model dynamics is sigma j a j x k, which I have already told you. Okay, this quantity is a bar plus b u k. So, when u k is this type, we have already said the closed loop system dynamics is given by this. Simply I replaced u k by this particular term, this is input. So, now assume that u j k is minus k j x k, such that jth linear subsystem is stable. Okay. This I am assuming such that jth subsystem is stable. Okay. If jth subsystem is stable, then the closed loop system dynamics is minus this will retain, this quantity is same, and this quantity is here, because this minus is coming here, u j k is minus k. So, minus terms is retained here, and sigma j this quantity is this quantity is retained here instead of u j k minus k j x k. All right. So, that gives you, if you look at that, that gives you the final value here, because this is b k j I can multiply, and then this becomes a j minus b k j, sigma j is common, and this side x k and this side x k. So, this is my closed loop dynamics. So, what implies that the common input matrix makes our closed loop system dynamics is very simple. This is very important. So, if we denote a j minus b k j by a j dash, the closed loop dynamics becomes this particular thing, where a j dash is a j minus b k j. We can design k j's in such a way that a j dash are stable. Okay. So, now the point is that we have designed, we can find u k in such a way that a j dash are stable, but now x k plus 1, this is the closed loop dynamics, this is the closed loop dynamics. So, my stability simply depends, I know already aj days are stable. So, now given aj days are stable, these matrices are stable, can I say that if I write this one as A bar x k, where A bar is simply j equal to 1 to m sigma j a j dash. Since dash is there, I will put this dash also here. Okay. So, A dash bar. So, if I say, can I say if a j dash are stable, then A bar is stable. You may say, oh, it should be, but it is not. If A z is stable, does not imply directly A bar is stable. Okay. So, we will find in this lecture what are the conditions for which if A z is are stable, then A bar is stable. Okay. So, that is the point. So, to show the closed loop system stability with common input matrix, we have to analyze the stability of this quantity and stability of this quantity where AJs are stable. Okay. This part I will not talk because this simply says that when the subsystems have different input matrices, then the closed loop the different, then if I find out, I designed ULK the individual systems as minus k Lx k, then x k plus 1 is given by this particular term, and you see that here we can't represent the way we represented. The reason is the above equation shows that there are cross terms in the closed loop dynamics when j is not equal to L. All right. And because of this cross terms that is coming here, because if it had it been B, it is simple, but it is B j. So, this makes our life little tough. So, now we will go to the actual stability analysis. So, stability analysis is common input matrix that we have now simplified. The closed loop dynamics for discrete time case is x k plus 1 is sigma j a z dash x k, and where a j dash is simply a minus b k j. Okay. So, k j is the associated state feedback for jth linear subsystem. So, the closed loop dynamics for continuous time case, similarly for the exactly this is discrete time. So, this is my the closed loop dynamics of the continuous time, where a z dash is a j minus b k. We will now provide various theorem which will ensure stability of this quantity. Okay. So, that is we would like to say, because now this can be written as a bar x k, and this can be written as a bar x t. So, if a j dash is stable, can I say a bar is stable? This is the theorem. So, stability analysis theorem 2, for discrete time T s fuzzy system x k plus 1, this is my T s fuzzy system with common input matrix with U k is given in terms of fuzzy blending of individual control action, and the control action is taken in such a way that individual subsystems are stable, then the closed loop system x k plus 1, which is given by this, is stable if the singular values of individual a j dash are less than unity, where a j dash is a j minus b k j. Okay. So, here the proof is the induced Euclidean norm or second norm of a real matrix A is given by A second norm, the induced norm is the maximum singular value of A matrix. And what is that? The maximum singular value of A matrix is computed as the maximum eigenvalue of A transpose A and take the square root. So, I compute the maximum eigenvalue of A transpose A and take the square root, then I find maximum singular value of A, where alpha max A is the largest singular value of A and lambda max A transpose A is the largest eigenvalue of A transpose A. Fact 1, singular values of a real matrix are real and positive. This is very important. Singular values of real matrix are real and positive. Fact 2, largest singular value of any matrix A is always greater than the magnitude of the largest eigenvalue of that matrix. It is very important. Largest singular value of any matrix A is always greater than the magnitude of the largest eigenvalue of that matrix. This is important. Okay. This I hope that you know this from the matrix algebra. So, now let us denote A bar dash as j equal to 1 to m sigma j a z dash. If all a z dash have singular values less than unity, right, then obviously the induced norm of a z dash, which is maximum value of a z dash is less than 1. Okay. So, this is so since alpha max a bar dash the largest singular value is given, because we are saying in the theorem if the largest singular value is less than 1 of all individual if individual matrix singular value of individual, the largest singular value of the individual matrix is less than unity, less than 1, then the system is stable. That is what we are saying. Okay. So, you see that now let me find out what is the largest singular value of A bar. The largest singular of A bar is induced norm of it, which is induced norm A bar dash is sigma j a z dash. A bar is simply this, and then you see that using triangular inequality, because these are summation. So, summation is summation of two product means by triangular inequality is always less than equal to summation of individual absolute product, that is sigma j a j norm. So, now I know this a j norm is represented by alpha max a z dash, and I know already that this quantity alpha max of a z dash always less than 1. I am assuming that. I know, let us say the all a z dash in this TS Fuzzy model, they have maximum singular value less than 1. So, because of that I can write this as, because this is quantity is less than 1. So, this is less than equal to sigma j, and you know that j equal to 1 to m sigma j is 1. So, this is less than 1. So, alpha max, the largest singular value of A dash is also less than 1, and we have already said the largest singular value is always, which we said earlier, you see that largest singular value of any matrix A is always greater than the magnitude of largest eigenvalue of that matrix. So, that is, since we proved the largest singular value of A bar is less than 1, means largest eigenvalue of A bar is also less than 1, and for discrete time case the largest eigenvalue, the magnitude should be less than 1, it should be unity circle. You know already that given a discrete time system, okay, the poles should be within the unity circle. So, what we said in this theorem, that if my individual subsystem in the closed loop form A z dash, they have a singular value less than 1, the maximum singular value, then the overall closed loop system matrix A bar also will have the singular value less than 1, implying that this system is stable. Okay. Now, utility of theorem 2, the proof of theorem 2 is based on maximum singular values, not on maximum eigenvalues. Utility of the theorem: making use of this theorem, the overall system stabilized if this system there exists a common input matrix B for all subsystem. The individual gain matrices Kj's are designed such that AZS, which I have already told is AJ minus BKJ, have singular values less than unity. This design techniques fails if the system is in controllable canonical form. In controllable canonical form, when all the poles are at origin, we can get minimum value of induced norm as 1. Okay. Stability analysis theorem 3. Now, earlier we talked about discrete time, now we will be talking about continuous time. For continuous time Ts fuzzy systems, x dot t is this quantity, which is our Ts fuzzy model. This is our normal fuzzy model with our again the control action ut is sigma j uzt and uzt is minus kj xt. The closed loop system x dot t is stable if the Hermitian part of AZS are stable, where AZS is AJ minus BKJ. Fact 1. Any matrix A can be written as A equal to half A plus transpose plus half A minus A transpose. Half A plus A transpose is known as Hermitian part of A. This is the Hermitian part. So, you can easily see that this total multiplication, this will cancel out. So, this is 2A by A 2A by 2 is A, but this is actually Hermitian part, this is non-Hermitian part. Fact 2, if half A plus A transpose is stable, then A is also stable, that is real parts of eigenvalues of A are all negative. Fact 3, if A is stable, that does not imply that half of A transpose is also stable. The reverse is not true. Okay. If this is stable, then I can say A is stable, but if A is stable, we cannot say A plus A transpose is also stable. So, proof: the matrix measure gamma corresponding to the Euclidean norm of a real matrix A is defined as that the maximum eigenvalue of the Hermitian part of the A. Since A transpose A by 2, the Hermitian part of A is a real symmetric matrix, its eigenvalues are real. So, if the Hermitian part of AZS is stable, that is half AZS plus AJ dash transpose is stable, then the matrix measure of AZS, which is the lambda maximum of this matrix, is always less than 0, the maximum eigenvalue. Since the matrix measure satisfies the triangular inequality, I can write the measure of my overall matrix AJ bar is gamma into summation j equal to 1 to n, and this is the individual AZS. And now, this can be written in terms of this is less than equal to, I can take this gamma inside using triangular inequality because the summation, and so the individual is sigma j gamma AJ dash, okay, because matrix measure satisfies the triangular inequality by using that theorem. So, we can say that this is less than this, and since I know that the matrix measure of this is the maximum eigenvalue of this quantity, which is always less than 0. So, and sigma j is always greater than 0, and this is a negative quantity, this is a negative quantity, this is a positive quantity, the summation will be always negative. Hence, the proof is if this is stable, AJ bar is also stable. So, the theorem, second theorem says for linear subsystem, continuous time system, the overall fuzzy blending of the systems will be stable, provided the Hermitian part of the individual subsystems. So, this is my Hermitian part of the individual subsystem, that is stable. So, utility of the theorem: making use of this theorem, the overall system can be stabilized if there exists a common input matrix B for all subsystems, and the individual gain matrix Kj are designed such that this has a stable Hermitian part. So, we can always design this, because I can always design such that this is a stable Hermitian part. It is not a difficult thing. So, limitation of theorem 3, if the subsystem are in controllable canonical form, Hermitian part of the overall matrix will be unstable. Okay. Consider a second order system like this, the Hermitian part is given like this, the characteristic equation is given, it is very simple. This implies that half A transpose A is unstable, this is an unstable system. So, if the subsystems are in controllable canonical form, the Hermitian part of the overall matrix will be unstable. Good news. However, for second order system in controllable canonical form, stability of individual systems is sufficient to ensure the global stability. Suppose individual systems are described by the following equation, the second order. Characteristics equation of jth system is this, thus the characteristic equation of overall system is this. For the subsystem to be stable, the necessary as well as sufficient condition is Aj1 and Aj1 must be positive. This implies that this particular summation and this particular summation are also positive. Hence, the overall system is stable. This is a simple logic. So, now we will go to theorem 4. For both discrete and continuous time T s fuzzy system, the closed loop system x k plus 1 which is given like this, or the in continuous time x dot is sigma j a z dash x t is stable if each individual a z dash matrix is symmetric, where a z dash is a j minus b k j. Proof: a matrix A is symmetric if A is A transpose. Thus, for a symmetric matrix A, one can write A is half A transpose A, that means it does not have a non-Hermitian part. If each individual A z dash is symmetric, then A z dash is half A z dash transpose plus A j for all j. In this case, the maximum eigenvalue of A z dash equal to the matrix measure of A z dash. Hence, the proof of the continuous time T s fuzzy system is similar to the matrix measure approach we used in the previous theorem. Again, for symmetric matrix, singular values equal to magnitude of eigenvalues. Therefore, the proof for discrete time T s fuzzy system is same as that of induced norm approach. Utility of the theorem: making use of this theorem, the overall system can be stabilized if there exists a common input matrix B for all subsystems and the individual gain matrices Kj's are designed such that Az is equal to Az minus Bkj are symmetric. So, now we will skip these things. Now, we will give some simulation results for surge tank. The output of the system is the level, the liquid level, which is to be controlled by input flow. Input can be positive or negative. Discrete time dynamical equation of a surge tank is Hk plus 1 is Hk plus T, and you can see that this is a nonlinear dynamics, and also Uk upon root over 3 Hk plus 1. This is the first order system. The system can be made stable by designing stabilizing control for different fuzzy region. So, you see that what we did, that we used a fuzzy neural network to identify these T s fuzzy model. You see that there are the system is identified using the input output model. The output range was 0 to 10, number of fuzzy clusters are 5. So, the 5 rules. T s fuzzy model of the system is described by following 5 rules. If x k is around 2, then x k plus 1 is 0.98 something plus 0.0032 UK and so on. Rule 2 is if x k is around 4, then x k plus 1 0.991423 x k 0.003928. So, like that you can easily see, although B matrix is varying, but almost similar. That is why the method that we said is also applicable here. So, the result of system identification, we generated data from the surge tank model, trained a fuzzy neural network, and you see that the data, the trajectory, the desired trajectory and the predicted trajectory, they exactly match. Okay. So, applying the global control, the overall system becomes like this, where the individual subsystems is controlled by state feedback. Okay. And Individual KL designed for this system meets this criteria, hence the controller stabilizes the global system. Since the overall output Hk is this quantity, the output here is Hk, Hjk is the jth subsystem output. If each individual subsystem tracks a reference input R, then the overall system will also track R. The controller thus becomes, you see, this is our state feedback part and this is my part for tracking. So, where Kj and J are feedback and feed forward gains for jth system to track the reference input R. Okay. So, the simulation results is presented in the following figure. The left figure shows the output of the system and the right figure shows the corresponding input, that means the control action, and this is my the height. So, I am tracking, I am set point tracking from 4 to 1, again 4 to 1, and this is very perfect tracking, you can easily see, and controller is almost very smooth. Okay. And you see that the gains, that the feedback gain and feed forward gain that were obtained, you can easily see here they are a time varying nature, because this is a nonlinear system, it cannot have a fixed gain, constant gain, it has a time a variable gain. So, variation of state feedback gains against this system state is also shown in the following figure. Now, we take the second example, which is a Van der Waals oscillator. Most of you have studied this in the introduction to nonlinear system, because it is a very classic example of a nonlinear system. X1 dot is X2, X2 dot is this quantity, and Y is X1, single input single output system. Okay. And if I linearize this system, I have this particular form, and you can easily see my B matrix is 0 1, my B matrix is 0 1, and hence this is common for all subsystems, and in the A matrix also 0 1 is common for all subsystems, only the second row they vary according to x1, x2 and x1 square. So, we can linearize that, and one example is if xt is around 0, then x dot t is 0 1 minus 1 2 xt 0 1 ut, and similarly we have 49 rules. Using this, the controller is designed. Okay. The tracking is achieved by placing the closed loop poles for all subsystems at minus 3 and minus 3.5. The feed forward gain is same for all subsystems. Thus, the control action is given by the following equation. Okay. And you see, this is my state feedback controller for regulation, and this is my tracking the reference signal. Okay. So, the tracking result, you see, the tracking is very very perfect, very good tracking given set point variation, and this is my control input. So, the simulation result is presented in the following figure. The left figure shows the output of the system, the right figure shows the corresponding input. This is my control action and this is my output. Okay. So, variation of the state feedback you can easily see again, the gains are variable, it is not a flat surface, there is a variable gain for K1 and K2. Okay. Summary: in this lecture the following topics have been covered. A general nonlinear system is represented as a TS fuzzy model. Local linear model parameters of TS fuzzy model are identified using a fuzzy neural network. Different theorems have been presented to ensure stability of the closed loop system when the subsystems have a common input matrix. In this case, the global controller has been designed as a convex combination of the local linear controllers. Simulation results have been presented for two nonlinear systems. That is all. Thank you very much.